Good evening once again, viewers. I am the Heavy Metal Chemist. I shall once again apologise for the significant delay in making this video, but I've been busy doing other stuff and, yeah, life kind of gets in the way. But I'm going to do something a bit different tonight. This is kind of a bit of a history lesson, general interest type thing. So not specifically related to chemistry, but I'm going to talk about the history of temperature and how people have measured temperature and how we measure temperature today, and a few interesting facts about it, and hopefully it'll provide a nice insight into a bit of the history of science and technology, which it's a hobby of mine. I enjoy reading about it, and it's really quite interesting. A few friends of mine study it, and it makes for a good conversation. So we need to go back initially to 1724, when a guy called Fahrenheit, you might recognise that name from the Americans use this temperature scale more than everybody else. He invented a scale, so let's draw a line to represent our scale. A line there with 0 degrees Fahrenheit. And this is the temperature which is reached by a mixture of ice, water, and I think it's ammonium chloride. It corresponds to minus 17.8 degrees C for us normal people. Why he picked that particular mixture, I have no idea, but that's what was defined as 0. And then defined another point at 32 degrees Fahrenheit. This is the melting point of water, so when water turns into ice, or ice turns into water. And then a bit further along we have 96 degrees Fahrenheit. This is what was defined as blood temperature, or around about 37 degrees C. It's a little bit higher than that as we measure it nowadays, and if we go up the scale even further, they then defined 212 degrees Fahrenheit as the boiling point of water. So the distance between there and there is 180 degrees Fahrenheit. Now, it's a bit of an odd scale. I'll just put a big F next to that so we know what we're talking about. And then, not long after this, some guy came along, his name was Celsius, and he thought, I know, this is a bit silly. So he came along with his own scale. We'll draw another line here to represent the Celsius scale, which then runs from there to there, from 0 to 100 degrees C. And that gives us the Celsius scale, so 0 being the melting point of water and 100 being the boiling point of water, which really is a far more logical way of doing things. But then as years progressed and we started discovering new things about how to make things colder, we reached a point where it was like, well, these minuses are getting quite silly now. We can go down to minus hundreds of degrees. So somebody comes along, takes the Celsius scale is a fairly logical scale to use. So let's draw another scale. And this was by a guy called Kelvin, which starts at 0. This 0 is absolute 0. And the size of each degree Kelvin, well, they're not called degree Kelvin. Kelvin is the standard unit of temperature used nowadays. A Kelvin is equal to a degree C in the magnitude of its difference. So 0 is equal to minus 273.1 something degrees C. So if we extended this scale down to 0 Kelvin, that number would go there. And basically this scale works upwards, so the melting point of water would be 273 point ... and the boiling point of water would be 373 ... point Kelvin. And room temperature is conveniently around about 300, a little bit less than that, 292, 293-ish if you want to be comfortable. But if you go to the tropics, it's around about 300. And there is another scale which people do sometimes use, which is called the Rankine scale, which, similar to this, uses Fahrenheit starting at 0 and working up to 400 and something for the melting point of water and 600 and something for the boiling point of water. Now the it's quite easy to convert from Celsius to Fahrenheit or centigrade to Fahrenheit. This is the degree C scale has been known as Celsius for quite a while, but it was originally known as the centigrade scale. So the two are sometimes used interchangeably, especially by older generations. It's quite easy to convert from one to the other, given you've got 180 there and 100 here. You can just plug it into Google and it'll give you the formula. It's times by 9/5 and add 32 or take 32, one of the two. So that's a brief history of temperature scales. Now the other thing I want to cover is kind of a bit of physics really, but it's still quite interesting. So if I draw another scale, this is going to be using Kelvin. So we're going to start at 0. Now 0 represents absolute zero. That's when nothing happens really. It's cold, really, really cold. Nothing moves. Atoms don't move, and generally it's a pretty abysmal place to be. And it's very, very hard to get down to that temperature. We can get close, but we really can't get there exactly. So let's say we take 1 Kelvin. What's happening at 1 Kelvin? Well, most materials are solids at this point. It's still bloody cold. Helium is just about becoming a liquid at 1.5 Kelvin, and not much else is happening really. So say we take 10 Kelvin as the next order of magnitude up. This is when hydrogen starts to melt, and some of the outer planets in the solar system are around about this temperature, between there and 100 anyway. 1 Kelvin, by the way, is around about the temperature of the universe as a whole. It's pretty cold, but still a lot warmer than absolute zero. So we go up to 100 Kelvin. This is around about the temperature of liquid nitrogen. You're starting to get to the temperatures of the inner gas giants, so Pluto's around about this temperature. As you get further in towards the sun, it starts to warm up. So this is kind of between here and 1,000. This kind of area is where most of the things on Earth happen. The coldest temperature ever recorded on Earth, I believe, was about -80, which is 180 Kelvin. And up to 1,000. Sorry, that should have an extra 0. That's 1,000 Kelvin. That's when most elements are starting to get a bit hot. Chemistry starts to happen really, really quite vigorously. Fire, things like that. So let's add another 0, because we can always add more zeros in physics. To quote XKCD, that's one of the fun things about it. But this is the temperature that you're starting to get the outsides of stars, hot plasmas that we can generate in labs on Earth. By this point, most chemical compounds have broken down and have turned into plasma themselves. It's generally when things are starting to get really quite hot. Nothing nuclear is happening yet, but we're getting to that. So let's go with 1,000,000 Kelvin. This is a point when nuclear fusion starts to happen, so the temperature in the centre of the sun is 15 million Kelvin. That's when hydrogen atoms stick together to make helium, which is what keeps the sun shining. And then we can keep going, so 10 million Kelvin. This is more like the temperature in the sun. It's 1 million kelvins when fusion starts. 10 million kelvins our sun. 100 million Kelvin is bigger stars, which start to fuse heavier elements, and when our sun runs out of hydrogen in its core, it'll start to fuse the heavier elements, helium, into carbon and oxygen. And then you can basically just keep adding zeros to the bigger stars. You start reaching kind of maybe several billions of Kelvin in the bigger stars, and then there are some ridiculously high temperatures for weird physics things that I really don't want to go into because they're far too confusing even for me. So I hope that's provided an interesting insight into a bit of history and something a bit different from my usual chemistry topics. If you have any questions, please do get in contact with me, either by Facebook contacts or sorry, not by Facebook, comments, or message me on YouTube or whatever. Like, subscribe, etc., etc., and I'll try and post some new videos soon. If you've got any requests, stick them on there, and I'll see what I can do. Thanks for watching, and have a good evening.